G'day chemistry students. In this video we are continuing to look at 7.2.2 and 4, 7.4.1 and 2, 7.5.1 and 2. All of the dot points which are focused on the properties of organic compounds. Today we're going to be looking at some of those factors, the way in which they influence the properties of organic compounds. That's going to start informing a lot of discussion and practice questions that we'll be completing in class. Let's get into it. What I want to be discussing first are the types of intermolecular forces. These are the main drivers for a lot of the physical properties that we see in our organic chemicals. Now we can categorize them into three core groups. First off, I want to look at dipole-dipole forces. What can happen between two elements in a bond is that there is the formation of partial charges. This is completely dictated by the electron negativity of the elements. So, for example, here in a hydrogen and chlorine bond, the chlorine has a higher electron negativity than the hydrogen does. What that means is it is more capable of pulling electron density towards itself. Now, it's not strong enough to rip the electrons away and form an ionic substance. It can't do that. But within a covalent bond, it can pull the electrons closer to the chlorine so that they spend more time on the chlorine side than the hydrogen side. That gives the chlorine a partial negative charge and the hydrogen a partial positive charge. Now, there can be an attractive force between those dipoles that form in those molecules, and that is an attractive force, and that attractive force will have an influence over physical properties. Hydrogen bonding is very similar. It's a type of dipole-dipole force, but this occurs between covalent bonds like an oxygen-hydrogen bond, in which the difference in electronegativity between the two elements is greatest. What this means is that the partial negative and the partial positive are as large as they sort of can be before we start to hit that ionic stage, and the attractive forces between molecules is therefore stronger as well because the sizes of these partial positives and negatives are large as well. We then also have dispersion forces, which can also be described as induced dipoles. This is where we have elements with either the same electronegativity, so that could be like a carbon-carbon bond, for example, so two carbons bonded together. Could be a substance with similar electronegativity, so that would be considered to be something like carbon and hydrogen as well. Now, these elements aren't really capable of pulling electrons in either direction in their covalent bond. What can happen, though, is that one of the bonds at some point, just due to chance, may end up having a partial positive or negative, that the electrons move to one side of the bond. If that's the case, and there's a positive charge on a bond in a substance, this can attract electrons which are on another molecule closer towards it, and for a moment can induce a momentary dipole. So there can be some attractive forces still, even if there isn't big differences in electronegativity between elements in a bond, but these forces are significantly weaker compared to the hydrogen bonding and the dipole-dipole forces. And most of that is because these forces don't exist permanently all the time, unlike hydrogen and dipole bonds and forces, which are present at all times. So for hydrogen bonds, they have the strongest bond strength. We consider them to be polar. And for organic bonds, we're looking at OH and NH bonds. These bonds are what lead to some of the strongest intermolecular forces, and that will have a large impact on physical properties. Dipole-dipole forces have strong bond strengths as well. They do lead to some polarity and some strong intermolecular forces. Some examples of some dipole-dipole forces in organic substances: carbon-oxygen bonds, carbon-nitrogen bonds, and carbon-halide bonds as well. However, our skeleton, the carbon-carbon and carbon-hydrogen bonds, have relatively weak intermolecular forces and are considered to be non-polar. These things will have an influence on our properties. So the types of intermolecular forces in an organic chemical will have an influence on some properties. Things that have hydrogen bonding will end up having a higher boiling and melting point. An example being here butanol. This is where the hydrogen bond is on the hydroxyl group. And there's a higher boiling and melting point because the intermolecular bond between each butanol particle is stronger than other organic chemicals, which means that they're able to hold together more and it requires more energy for the substance to melt or boil. Butanol will also have solubility in water. The hydrogen bonds are polar, and we already know that when we are dissolving substances, polar substances dissolve into polar substances, non-polar substances dissolve into non-polar substances. For things with dipole-dipole forces, they will have a lower boiling and melting point than something that has hydrogen bonding. An example here being the dipole-dipole forces in diethyl ether. Remembering that we don't focus too much on ethers really in this topic, it's just the example that I've got here. But for this one, there's just a dipole-dipole bond between the oxygens and the carbons. But because the intermolecular forces between this molecule and another diethyl ether molecule are weaker than the intermolecular forces for the butanol, the resultant boiling point is lower. It will also have a reduced solubility in water. Now, for something with dispersion forces, we know that their boiling and melting points are going to be lower, and that's because the attractive forces between molecules are as low as they can be, and those substances will be insoluble in water because they are non-polar. Chain length can also have an influence on properties as well. So there will be an attractive force between molecules at their carbon-hydrogen bond along the chain. This attractive force is a dispersion force, but the forces are additive, meaning that if there are more bonds where potential interactions can occur, there will be more interactions, more pulling force, more attraction. Now, if this is the case, then if we were to compare our butane to our octane and their boiling points, we should see that the butane has a lower boiling point and the octane has a higher boiling point. We should also note, and I'll show you some other examples in class, but the longer a chain, the more non-polar the substance becomes. So for example, if our two substances were butanol and octanol, we should find that butanol is more soluble in water because the hydroxide part should still be able to allow the substance to dissolve in water despite having a non-polar part of the chain. In comparison, the octanol should be significantly less soluble in water because even though there might be a hydroxyl group present, most of the substance is actually non-polar, making it very hard for the water to dissolve it. So there's our relationships there. Long chains have higher melting and boiling points. Short chains have lower melting and boiling points. And there's a few stats here for comparison. When we're looking at solubility, longer chains make substances less soluble, even if there is a polar component, a polar functional group. And shorter chains allow that polar functional group to actually dissolve in water effectively and make the substance more soluble. Now, steric factors can also have an influence over the properties of a substance as well. When we're looking at our two chains here, both of them have 4 carbons total in each molecule. However, my straight chain here, my butane, is flat and allows for lots of dispersion forces between the two molecules. In comparison, on the other side, I have 2-methylpropane. And what we can see is that there isn't really a lot of space for interactions between our carbon-hydrogen bonds. When we use this term sterics, what we're referring to is the space that each molecule occupies and the effect that that has on physical properties or the way that it reacts. So essentially, if the molecule can be arranged in space in a way where our bonds are easily able to access each other and interact, versus an arrangement which inhibits the amount of interaction between bonds, the stronger the attractive force between the molecules will be. And in this case, we'll have an increased boiling point because there is a larger attractive force compared to a decreased boiling point for molecules in which the geometry is not favorable, it's not flat, and it's all over the place. In terms of solubility, these ones probably won't make too much of a difference. Certainly for these ones, because they'll both just not be soluble in water. However, if we start looking at functional groups and the way that they may be exposed or inhibited, we may see some impacts on both boiling point as well as solubility. So here I have a primary, secondary, and tertiary alcohol. So primary there, secondary here, tertiary in the bottom corner there. What we should see with our primary alcohol is that the hydroxyl group is actually quite exposed, meaning that interaction between hydroxyl groups should be quite easy. The hydroxyl group is also accessible for water, meaning that it will have a high solubility as well. In comparison to our secondary alcohol, what we should be able to see is that the hydroxyl group is a little less accessible between our alcohol molecules. And as well, this would make it a little bit more difficult for water to be able to sort of latch onto that hydroxyl group and effectively dissolve it, effectively decreasing the solubility of the alcohol, despite both of these being butanols. When we look at our tertiary alcohol, we have 2-methyl-propan-2-ol. So they still have the same molecular formula. They're just an isomer of each other. However, what we see is that it is very difficult for the hydroxyl groups to effectively interact. They are quite inhibited. What that's going to mean is it's going to be really difficult for water to be able to interact with those hydroxyl groups, meaning that this has the lowest solubility of our three isomers, our primary, secondary, and tertiary alcohol. We can apply similar theory to boiling point. I'm hoping that we can appreciate that for the primary alcohol, because it has the most interaction between the hydroxyl groups, it has the highest boiling point, followed by the secondary alcohol, and then the tertiary alcohol has the lowest boiling point because of the limited interaction between the hydrogen bonds. The following image just gives a slightly different, less complex visualization of what's happening. If we have branching, it's going to be a lot more difficult to be able to have our carbon-hydrogen bonds interact effectively. And a similar thing can happen when we're looking at functional groups, depending on how exposed the functional group is for interactions with other molecules. Thank you very much, everyone. In the next video, we are going to be focusing on using organic chemicals, both in the lab and in society in general. Our focus is going to be primarily on safety and handling, and will be an introduction to using organic chemicals in the lab so that we can start doing some experiments with them. But until then, have a good one.